Alright, so we're working on a new set of notes, and let's see, I better stop doing that or you're what we're doing in the last video is we just finished the spectral theorem, and I incorporated some more coding, and so some of the pages have changed, and so the spectral theorem is now on page 50. And so if you're going along with the book or the notes, that's a good place to start, is page 50 of the notes, and we'll just review the spectral theorem before we get started on the new stuff. Good. So the main thing with the spectral theorem is it says that if A is symmetric, that is, if A is equal to A transpose. By the way, this is for real and symmetric. Our matrices are all going to be real, so if it's complex, you have to do something a little bit different. But so for us, we're going to say A equals A transpose, and that means that that's the kind of matrix we're going to be working with. And for symmetric matrix, A is said to be orthogonally diagonalizable. What does that mean? That means that it's the result of the spectral theorem. A has n real eigenvalues. That's really nice. For each distinct eigenvalue, the algebraic and geometric multiplicities are the same. Therefore, symmetric matrices are not defective. Symmetric matrices are not defective. That's always nice. Good. The eigenspaces are mutually orthogonal. Another way to think about this is the eigenvectors, the evects, are all orthogonal to each other. And in fact, we're going to normalize them as well. And so the evects are orthonormal. They're going to provide an orthonormal set. And so that's what we're going to mean by that orthogonally diagonalizable. A can be factored as V times D times V transpose, where D is a diagonal matrix with the eigenvalues along the diagonal, and the vector V, or sorry, the matrix V corresponds to the eigenvectors. By the way, be careful here, because V1 corresponds to lambda 1, right? Then V2 would correspond to lambda 2, V3 corresponds to lambda 3, and so on. Good. All right. And so furthermore, because the vectors are all orthonormal, right, that means that V transpose is actually V inverse. All right. Finally, before we leave the theorem off, there is a nice way of writing this product, and I'm just going to briefly touch on that. I guess I'll have to use the notes in the book, even though, or notes in the notes. So just a quick little proof, and that is that eigenvectors, evects, corresponding to distinct evals are orthogonal. And so that might be interesting just to see why that would be true for symmetric matrices, but not true for other types of matrices. And so the way we're going to do that is we're going to let lambda 1 be not equal to lambda 2. Those are going to be our distinct eigenvalues. And we're going to show that the corresponding eigenvectors are orthogonal, which means that we're going to show that the dot product is equal to 0, right? Good. And so the way we're going to start is we'll just start with consider lambda 1 times V1 dotted with V2. Okay, so now I'm trying to show that that's equal to 0. I threw in this lambda 1 here because we can now substitute this in for my matrix A, right? That's AV1 dotted with V2, right? And that's equal to, the dot product is the transpose, right? So that's AV1 transpose times V2. When you take the transpose product, the product of the transpose of the product, you have to go in reverse order. So that's V1 transpose A transpose V2. And here it is. This is why a symmetric matrix works so well, because we can replace A transpose by A. And so that's equal to V1 transpose times A times V2. V2 is an eigenvector, therefore that's equal to lambda 2 times V2. And there's your proof. This is lambda 2 times V1 dotted with V2. So all we've done so far is we've shown that lambda times V1 dot V2 is equal to lambda 2 times V1 dot V2. And so bringing those over to the other side, I'll have lambda 1 minus lambda 2 times V1 dot V2 equals 0. Good. This means that either lambda 1 minus lambda 2 equals 0, or V1 dot V2 is equal to 0. Good. Is lambda 1 minus lambda, or sorry, let's let's start with the constants. Is lambda 1 minus lambda 2 equal to 0? No, because this is by assumption, right? So therefore V1 dotted with V2 must be 0. So therefore the eigenvectors must be orthogonal. And see, why I did this proof for you is that the symmetry was really important. This step right here, excuse me, this is a key step, and it relied on A being a symmetric matrix. So if A was not a symmetric matrix, we would not be able to make that step. Good. All right. And so for the spectral decomposition, I just wanted to make a note about the notation here. Note about the notation. What does V transpose look like? I'm going to change the notation slightly from the notes because I'm using V's and D's here. I don't know how I switched to Q's and lambdas. Well, the D is the set of lambdas, right? And just to let you know how to work this notation, how does this notation work here? Right, if I take this diagonal matrix times this matrix, what I end up with is V1 Vn times, this is going to be lambda 1 V1 plus 0 all the way down, so that's just going to end up with lambda 1 V1 transpose down to lambda n Vn transpose. And so now if I expand this product, I get V1 times lambda 1 V1 transpose, which is lambda 1 V1 V1 transpose. This is not a dot here, by the way, that's just multiplication, plus lambda 2 V2 V2 transpose, okay, up to lambda n Vn transpose. Good. Now you might be saying, well, what's the deal with that? Well, the key here is that this is an n by 1 times a 1 by n, so this is an n by n matrix. And so this whole thing is a sum of matrices, right? And in fact, to go even further, these are actually rank 1 matrices. That's not hard to prove, but so we've broken down our large matrix into a sum of very simple matrices. Well, our matrices was a very simple structure. Okay, and so we're going to actually program these in. I think I've got the programming done in the programming exercise. Yes. So this is examples are programmed in the programming on page 51 and 52. Okay, So that's a good exercise to take a look at, just so you kind of see. By the way, number 1 in the exercise section on page 51 says the following: prove that if x is invertible, so x is just any invertible matrix, and A is square, then A and x inverse. Oh, oops, got those reversed. Do you think it's going to matter? I don't know. Have the same evals. That's not too hard to prove. But I will say that just to get you started on that, how would we prove this? So we would start with letting lambda be an eval of A. And then we would have to show, well, by the way, that means A times V, right, is equal to lambda times V. And now somehow we need to show that lambda is an eval for x inverse AX. I'll let you think about how that might be done. There's might be a little bit of a trick here. So maybe a little hint. Can we write V as W times U for some W? Yeah. Or is that going to be too vague of a hint? Oh, I'll just give it to you. X times U. Is that going to be valid? Okay. I'll let you think about that. Good. Okay. I'm out of time for this video. And when we come back, we're going to be starting in on page 52. So, next video, we'll start on page 52. The SVD, one of the highlights of any data analysis.